I'm Courtney Ultram.
And I am Davey Winter.
And we did our project on MotoGP analysis. If you're not aware of what MotoGP is, it's basically NASCAR for motorcycles.
So starting off our presentation for you guys, we're going to start with our motivations and goals pertaining to our project. What we want to be able to do is we want to be able to display and analyze the statistical data for the MotoGP Grand Prix race of Qatar 21. The race this year, and it is the first race for the MotoGP World Cup, the opening one. We also want to be able to go and display in that data, such as information as the rider and the bike's information pertaining to that rider, speed of a bike at a particular moment in the race, such as down the track at one point, as well as information about the track, which in this case is the Losail International Circuit in Doha, Qatar. We also want to be able to allow people who are fans or data experts to be able to use the information for statistical analysis or personal enjoyment.
So some background information. If you're not aware of like the physics of motorcycles, they have to slow down a considerable amount before they enter corners, so that they can stay on track and not fly off the track. So this for the Losail International Circuit, here's an image of it on the right here, and it has 8 turns where you would need to apply some sort of braking before entering the corner. So on turn number 1 here, for example, you would be coming in from this straight here on, like, say, the second lap at 357 kilometers per hour. You would need to slow down to about 108 kilometers an hour before you started the curve in order to stay on track. And that takes around 263 meters or around 5 seconds of braking time. And that produces a force of 1.4 Gs for that deceleration. So the corners of a track in races like these are really important because how fast you can complete the race really depends on how fast you can take these corners at.
Here is our ER diagram for our tables in our database. The first one I will talk about is the rider table right here in the middle. It pertains to stuff such as the rider and their motorcycle last name, first name, kilometers per hour number. And it has a one-to-many relationship between race, where there's many races, the points on the track. It's a very huge table, like 1,700 rows or something, where it's the points on the track for that rider where they're going. So it's a rider at one point on that track, and then say like another unit of time later for how many meters that they have. As well, we have turn up here, which doesn't relate to anything, but it includes information like Courtney mentioned for how you can take the turns, how fast you can take them, the brake time, things like that. As well as rider has a one-to-one relation between the lap time, which the lap time includes the T1, T2, T3, T4, and the total for the lap time. Those T1, T2 things such as those are points along the track, which are major points along the track, which are recorded for the times, as well as the total, which includes all of them and is a full lap. Now, rider also has a one-to-one relationship between motorcycle, which is it's the rider's motorcycle. It'll also include things on that motorcycle such as the make, the model, the mass, just the basic information about a motorcycle that a rider could be handling in that particular race. There's also a one-to-many relation between acceleration and motorcycle, as many motorcycles could have the same acceleration going. And then, Courtney.
So here's an example of our tables. So in MLPQ, so here's our turntable. It includes ID, initial speed in kilometers per hour, final speed, which is the speed you need to take the curve at in kilometers per hour, the stop distance in meters, and the brake time in seconds. So here's an example of how the first corner would need to be taken. You would need to take about 260 meters to stop or to brake, and that would take about 5.1 seconds to break from 359 kilometers per hour to 108. Next example we have here is the rider, which has position, which is where they finished in the race, their number, their first name, last name, what team they're on, what motorcycle they're racing with, their total time that they completed 22 laps, and their average kilometers per hour. Next, we have motorcycle, which relates back to that rider number, has a make, a model, a mass in kilograms, an engine configuration, power and horsepower, acceleration in meters per second, and a top speed in kilometers per hour. For lap time, we have a rider number, T1, T2, T3, T4 in seconds. Like Davey said, these are officially recorded by MotoGP as certain intervals on the track. And then we have a total in seconds for how long a rider took to complete a lap. Next, we have acceleration. This is a moving objects representation. So we have a bike with the make. This is a formula for velocity, which has to be less than the top speed. And we went from 0 to 10 seconds because it takes about 10 seconds for these bikes to reach 300 kilometers per hour, which is a little bit less than their top speed, but right around there. And last, we have race, which is, like Davey said, those are those points on the track. So you have the rider number, what speed they're at in meters per second, the time, and how many meters they've completed in the race. So at 1 second, rider number 12, which is Maverick Vinales, is going 9.21 meters per second and has traveled 9 meters in the race.
For our data sources in our project, I will go and show it soon, but we also have an image of the track, which we use the I2V2C MATLAB script provided to be able to go and trace along the outside and then the inside of the track to be able to create a constraint database representation of that track. The timings that we have gotten are provided officially by MotoGP by TSUT for information about those, as well as about riders. As well, Courtney had an image earlier, which was provided by Brembo about the braking and track information, as well as the MotoGP bike acceleration estimations were based on data from MC News. And then we just have a few of those links here, as I have mentioned. So here is the track that I was talking about. As you can see, trace the inner and the outer to be able to have a bit of a wider representation. So it's actually like a sort of road that somebody could physically be on, or a point on that. There's some of the MLPQ on the bottom that are shown from the I2V2 script for that, as well as in a bit, we interpolated points on that track for a rider for their estimation of going around that track. Like I said, we have a rider, and we use the Pline.m script, like the I2V2C script provided. We use the Pline.m script to be able to interpolate those points on that track.
Yeah, so continuing with our data transformations, so to get around a kind of a lack of functionality of basic arithmetic within SQL queries, we implemented a C program that calculated the speed distance of times riders in an ideal race. So it takes into account what speed you need to take the corners at, how fast you can get going in the straights, stopping distance, braking time, all of that. So that kind of deals an ideal race. It's not exactly what the race was, but it's a good representation of if you were doing the best that was possible, you could get this amount of time. So this C program outputs that data as MLPQ, and then we import that file into MLPQ along with our other tables. So we had to actually do a lot of physics calculations for this project, and we had to do a lot of estimation as well. MotoGP bikes are almost never formally tested for like acceleration or other capabilities because they're not meant to be available to the general public. So this data isn't available. But we did some calculations based on a basic kinematics equations and data that we observed from watching videos of these bikes, and we estimated an acceleration for each vehicle. There's also, fortunately, quite a bit of other data about these bikes, including top speed, which isn't really an indication of how fast these bikes can go, but of how fast a rider is willing to go on these bikes.
Now, as I have mentioned, we have as we've used the interpolation for our, we have an animation here that I'm going to be showing you, and a little bit of the MLPQ here at the bottom for how that moving object is going to travel around the track. And I will go ahead and show this. Hopefully, it is in good quality. It's a bit hard to see. It's still a small point, but he's going around the track, taking those corners slightly slower so he doesn't fly off. And he just goes around. So we've used our data here as well as interpolation. Let's play that again. It's a pretty cool animation of a simulation of a rider going around the track. There we go. And I don't know how this works. Okay, so here we go. We have some of our SQL queries. This first one is in a query for the fastest rider for the race. So we just have a nested query that is able to go and take the fastest lap time. And in this case, that is Francisco Laganaya with a total lap time of 121.260002. And then here's our next one for the fastest corner that you can theoretically take. It's another nested query, this time just from turn. And this will be there's actually three that come up with 260, and that'll be the turns of 11, 12, and 13.
So our next query selects how many motorcycles are Ducatis. So we select count from motorcycle, where motorcycle make equals Ducati, and there are 6 Ducatis in this race. And for our last query, we're selecting how many meters are completed in the race at 60 seconds for each rider. So we select the rider first name, their last name, and the meters in the race from race and rider, where the time in the race is 60 seconds, and the race.id equals the rider number. So here, we can just point out a couple examples here. So see Maverick Vinales is at 3,180 meters at 60 seconds, and Alex Rins would be at 3,093 meters at 60 seconds. So here's for conclusions and future work. We did have some trouble with animating the lap, or the animation of the rider going around the track. We think we could implement multiple riders going around the track, and that would be ideal. We could also analyze other races, such as the 2014 MotoGP race on this same track, Losail Circuit, other MotoGP races on other tracks, or even F1 races. And another thought that we had would be implementing the same project in a different database system, such as Oracle, and see the differences between Oracle and MLPQ and how implementation would be different.